Engineers, I wanted to make a quick video with this problem here. So it says I fill a pressure cooker full of water to the lid, 2 kilograms, and leave the lid open until the moment it starts boiling. Then I close the lid. At that moment, the volume is 2.086 liters. I come back a little later and the temperature reads 120 degrees Celsius. So what we have here is we have an initial state given, and then we're moving from that initial state to a second state. I want to be able to calculate both of those states and talk about the process in between. And we could also talk about how much heat was, or how much energy the pressure cooker used to add that heat to the liquid. So let's start. Starting with state 1, we can write our known. So it tells me that the volume is equal to 2.086 liters, and the mass is equal to 2 kilograms. And it also tells me I leave the lid open until the moment it starts boiling. What that tells me is that I am at the phase that we call a saturated liquid. So it's a saturated liquid, or the other way to say that is that the quality is equal to 0. If we think about our TV diagram here, and I draw my steam dome on it, this is my saturated liquid line, and this is my saturated vapor line, and I'm somewhere along this saturated liquid line in this diagram. So I'm somewhere over here on that TV diagram. So with the state postulate, I don't need to make any more assumptions here about what I have. I have two. The state postulate tells me I need two intrinsic variables, ones that don't depend on the mass. And so what I can do is I can figure out, I have the volume and the mass. I can figure out the specific volume, V, is equal to the volume divided by the mass. And if I do that calculation, I get 0.001043 meters cubed per kilogram. I don't even have to make any assumptions about the pressure or the temperature that it's at. If it's boiling, it doesn't tell me like what altitude I'm at, because I can just go right over here. Let me go over here to this table, the saturated water table, and I can look at this table and I can say, okay, well, I know I'm a saturated liquid, so I'm going to be somewhere in this column here. So if I just highlight this column, and I know what my specific volume is. It was 0.00143. Perfect, I just found it. I can read my temperature, my pressure, my internal energy would be, for the saturated liquid, would be 419.06 kilojoules per kilogram. I can get all sorts of information about my state at that point. So I could write down my state here. I could say, okay, the temperature is equal to 100 degrees Celsius. The pressure is equal to 101.42 kilopascals. The internal energy is 419.06 kilojoules per kilogram, etc. I could keep reading off those. I picked 419.06 because, again, I said I'm a saturated liquid, so I have to look at this column here. That tells me that all of those numbers are along that saturated liquid line. So that's my first state. State 2 tells me that the temperature is equal to 120 degrees Celsius, and we know that the volume, because the lid is locked, there's no, the volume's not changing, the mass isn't changing, so the specific volume should stay the same. So the specific volume should still be equal to 0.001043 meters cubed per kilogram. Now, a tricky thing about this might be thinking, okay, well, how would I describe the liquid in this? Is it boiling water? Is it still a saturated mixture? It started as boiling, and the temperature increased, so it'd be tempting to say so. But if we look at just these two pieces of information back here at this table for the saturated water, if we go down to 120 degrees, highlight 120 degrees down here, I can see that, okay, the saturated liquid line is 0.001060, and it only gets larger from there, up to 0.89113 meters cubed per kilogram. So I am somewhere, my specific volume is less than, at state, my specific volume at state 2 is less than V sub F. So I'm somewhere, if I look at this line, V, I'm somewhere on this side of the line. I started over here as a saturated liquid, and when I moved as a constant volume up to state, so this was state 1, as I moved as a constant volume over to state 2, I ended up somewhere to the left of that line, which means I'm not a saturated liquid. I'm just in this region over here, which is liquid water. And so I need to go to a different table to calculate my state. And the table that I need to look at is this one down here, compressed liquid water. And so what I need to do is I need to find, looking for temperature is 120 degrees. I need to find a number or pair of numbers that is close to my state. So I'm looking at my specific volume here, and I'm looking for 0.001403. And so if I look at this table, I'm at 0.0015. I'm getting smaller as I move. As I increase in pressure, I'm getting smaller. So coming down here, okay, it's getting closer, even closer here. Okay, and then we've passed it here. So it's somewhere between 30 megapascals and 50 megapascals is my pressure. And so I could figure out what it is. Let me write this down. We have these volumes at given pressure, at different pressures. So I'll make a little table here. I'm at 0.00104445. My pressure is 30 megapascals, and at 0.00103449, my pressure is at 50 megapascals. And we know that my specific volume is 0.001043. And we don't know the pressure at that point. But we can just do a linear interpolation between these values to find the answer. So when I say a linear interpolation, what I mean is we have 2 points. So we have, like, if we have x1, y1, and x2, comma y2, we have this line that connects the two, and we're assuming that my midpoint is falling somewhere in the middle here. There's 2 ways I could write this formula. I could write the equation for a line, y equals mx. So this is, I'll call this y. I'll call this x question mark, comma y question mark. So y question mark equals mx question mark plus b. So the equation for the line, well, my slope is just going to be the rise over the run. So plus my x, and so here we actually have to write x question mark minus x1 plus my y-intercept is y1. That's one way I could write that equation. I have y2 and y1, x2 and x1. I have my x value, which is 0.001043. I can plug that in and get my y value. The other way that I could write this equation is just say that the ratio between these two values, between x1, y1, and x2, y2, is the same as the ratio between x1, y1, and x question mark, y question mark. So the way that I would write that is like this. I could say y question mark minus y1 over x question mark minus x1 is equal to y2 minus y1 over x2 minus x1. Both those are the same thing. You could get from one to the other just doing algebra. But I could plug in my numbers and get my unknown pressure. I'm just going to label these numbers to save myself some writing here. I have, this is going to be my y2, and I'll call this my y1, and that means this is my x2, and this is my x1, and this is my x question mark. So I could plug all those numbers into this formula here and get my y question mark, my new pressure, is equal to 33.125 kilopascals. And so I could plug that in to my state here. So my pressure that I just calculated is 33.125 kilopascals. And I could do the same thing to find the internal energy from this table. I could I could figure out all sorts of values from this table and get this state here. But that's how we can calculate these states using